Hi, myself Yogesh Landge, and in this video we will see a numerical which is asked in GATE examination 2022. So let's see the statement of this numerical. It is say the perfectly insulated double pipe heat exchanger is operating at a steady state condition. Saturated steam enters inner pipe at 100 degrees Celsius and leaves at saturated water at 100 degrees Celsius. A cooling water enters the pipe at 75 degrees Celsius and exit at 95 degrees Celsius. The overall heat transfer coefficient is 1 kilowatt meter square per Kelvin and the heat transfer area is 1 meter square. The average specific heat capacity of water at constant pressure is given 4.2 kilojoule per kg per Kelvin. The required cooling water flow rate is to be calculated. So this is the numerical which is not a MCQ one. Here if we have to write the answer in up to the 2 decimal points. So let's see how we can solve this numerical. It's very easy to solve. Okay, as here it is mentioned, it is as the double pipe heat exchanger is there. Okay, and in this one we can see the steam is given at 100 degrees Celsius, which is in. Okay, the outlet temperature is again the same for the steam. The inlet temperature for the water is mentioned, it is 75, and for the exit it is mentioned 95 degrees Celsius. So here we just have notations for it, inlet and outlet. The overall heat transfer coefficient is given in 1 kilowatt, so we need to convert kilowatt into the watt, so it is 1001, and the area for the heat transfer is 1 meter square. Also they give the specific heat of the cooling water, which is be 4.2, so in it is given in kilojoule. We again is modified it and convert it into the joule per kg. Now with the help of this data we solve a numerical. So let's see what are the steps involved in here. So we consider here a steady state condition. The first thing, we consider a steady state condition, and on the basis of this one we just solve the numerical. Okay, so here we say that as the inlet and outlet temperature of the hot liquid is same, so we are not worried about a co-current or whether the counter current. So here it is a double pipe one, so either we can take a co-current one or it is a counter current one. There is no matter, because in this case the inlet temperature is 100 for the hot water and outlet is also the 100, so and the cold water is 75 here and here is the 95. So either you take this side, there is no matter. Okay, whether it is a co-current or counter current. Even you can see here, let's see, this is 100, this is the 100 for the hot liquid, and for the cold liquid if we say it is a, say this is 75 and this is 95. So either you consider this condition or you consider this condition, it doesn't matter. Okay, then we will find the second step. We write the equation in terms of the overall transfer coefficient. So we are writing the equation in terms of the overall transfer coefficient like this: Q is equal to UA delta T Lm. Okay, so here we need a delta T Lm, so we calculate the LMTD with the help of the 4 temperatures, because of 4 temperatures are mentioned here. And then we will find what is the Q, that is heat rate through this condition. And then after that one we will write the energy balance equation by considering the cooling water. So here we can write energy balance equation, that is Q is equal to M, that is the mass flow rate of the cooling water, into the specific heat of cooling water and the temperature difference of inlet and outlet of the cooling water. Okay, so inlet and outlet temperature of the cooling water. So this is the way that we can solve and we get the value of this one, because we are asking what is the value of mass flow rate of the cooling water. Fine. So here what we do, first we are writing the equation as we mentioned in the previous slide. The steps involved here, we write the overall air transfer coefficient. So it is Q is equals to the U A delta T ln. Now we know the value of U, we know the value of A because it is mentioned. The U is mentioned, it is around 1000. Okay, and the value of A is given 1 meter square, but we do not know the value of delta TLM. So how we calculate the delta TLM? We can calculate with the help of the simple formula by considering, say, the co-current flow pattern. Okay, say this is the 100 inlet temperature of hot liquid, this is 100, which is the outlet temperature of hot liquid. Consider this is the inlet temperature of cold liquid, which is the 75. Okay, as well as the outlet temperature of a cold liquid, which is the 95. Okay, so here we write the delta T1. So the formula for the LMTD is what? LMTD is, it is log mean temperature difference, that is delta T1 minus delta T2 upon ln of delta T1 by delta T2. Now in this case what we do, we have a delta T1 is what? Delta T1 is here, it is the THI, inlet temperature of the hot liquid, minus inlet temperature of the cold liquid, as we consider the co-current flow. Then delta T2, it is the outlet temperature of a hot liquid minus outlet temperature of the cold liquid. So with the help of this one, we have the delta T1 value is 100, which we have taken from this one, minus 75, which is 25. Okay, similarly for delta T2, we have 100, the outlet temperature of the hot liquid minus outlet temperature of the cold liquid, which is 95 and which is 5 degree Celsius. So we got the value of delta T1 and delta T2. So just put it the value of delta T1 and delta T2 here in this formula. So it is 25 minus 5 upon ln of 25, that is delta T1 upon 5, which is the delta T2. So we calculate this LMTD value, and after calculation with the help of calculator, we can get the value of LMTD is 3. So here the LMTD value that we get, it is 12.426. So it is 12.426. Okay, so this is the value in degree Celsius. Now we will go for the next case where we want to calculate the value of Q. So we put it the value of U, A and delta TLM, and we get the value of Q, and that value of Q we get, so by putting Q is equal to U is 1000, A is 1 and LMTD is 12.426. So with the help of this formula, what is the formula? In terms of overall heat transfer coefficient, Q is equal to UA delta T LM. So we just use this formula and just put it the value, and we got a value of Q. After that one, it is 12426.7 watt. Okay, so we got this value around 12,426. Now what is the next step? After that one, once we calculate the value of this one, so we use the energy balance equation, and we consider here the cooling water, because we have the data of cooling water, and for that one we use it. So Q is equal to and again we need to calculate the value of mass flow rate of the cooling water. So it is Q is equal to M, that is the mass flow rate of the cooling water into the specific heat of the cooling water which is mentioned, and the temperature difference, that is the TCO minus TCI. Okay, so what we do, we have the value of Q from this one as we calculate. So we can write 12426.7 mass flow rate of the cooling water, that is to be asked. Specific heat is given, it is 4200, into the temperature. Outlet temperature is 95 as mentioned in the statement, and input temperature is 75. So once we calculate this one, after doing these calculations, we got a value of mass flow rate of the cold water which is around 4.1479. So we can round it up to the 0.15. Okay, so this is the answer. So you can write this answer either from mass flow rate is either you can write 0.14 to 0.15. So in between this range you can write any answer. You can write this answer, no problem, your answer is correct. Fine. So this is all about how to solve this simple numerical on the heat exchanger. Thank you.